So I'm just going to talk about my research and how it applies to, or how the things we are learning in this class apply to it. And hopefully you'll get a few practical tips also for implementing controls in your systems as well. So first, I'm going to give you a little bit of background about what the research scope is. And then the two examples of loop shaping are the linear amplifiers that I'm using to power the stage, and then the stage itself. The amplifiers, I think you're going to find very familiar from the design problem. Here is kind of a background about photolithography. It's the process that is used commonly to make computer chips. So you have a light source that is shown through a reticle, which has the pattern you want to imprint onto the silicon. And then you have a platform down here with a silicon wafer. The wafer might contain a few hundred computer chips. So you need to rapidly move the stage to scan this image on each chip. And then in the scanning process, you're actually moving as well. The features on the chip are, the paper I cited say 20 nanometers, but that's always getting smaller. And of course, we always want to move faster because we always need more computer chips. So we need to be very precise and also high forces. So it ends up being that these stages are almost always levitated, just so that you don't have mechanical contacts. So you don't have things like thermal and vibration disturbances messing up your features of the chips. Most of those levitated stages use Lorentz actuators, which we've talked about some in this class. This diagram, it's just like, this would be the copper coil that you'd run current through, and then you have magnets creating magnetic field. So just I cross B gives you your force. They're useful in that they're very, they have linear performance, so they're easy to control. But we've talked about in this class also that they have a kind of fundamental limit of the force they can produce, which is based off of the current you can run through the coils before the coils melt, essentially. So most of these stages use water cooling to run high current through the coils. Our research impetus was to create an actuator that didn't need water cooling and that could efficiently create some high forces for this type of application. This is a CAD model of the prototype actuator that was designed by a previous student in our lab, Tyler Hamer. And because the wafer is translating horizontally, the primary forces that you need are the horizontal plane, X and Y. So that's what this actuator is designed to produce. And the thought is you can integrate it with more traditional actuators for controlling the other 4 degrees of freedom. This is the copper coil. So there's 4 coils on the stator. And then this centerpiece, we don't call it a rotor because it's not rotating. We just call it a mover. And the blue and red indicates magnets, permanent magnets that we put to bias the air gaps. Then there's these steel flux guide pieces and then aluminum clamps to hold everything in place. Yeah, another interesting feature of our specific actuator is that the requirements specified a very large Z and theta Z stroke compared to only a 0.5 millimeter air gap in X and Y. So that was an interesting design feature that Tyler had to deal with. Looking more at the magnetic circuit behind things, which this is a nice drawing from Tyler, it kind of demonstrates how we can get higher force for this actuator versus Lorentz. Is you have these permanent magnets which are biasing the air gaps with magnetic flux. And then your coil flux just modulates the air gap. So you can see here, the net contribution is lower flux here and higher flux here. That flux difference creates a force, and the force is proportional to the square of the difference of the squares of the fluxes. So because of that squared value, you can get, if you bias the air gap, you can get higher force density as opposed to a Lorentz actuator. But a negative of that higher force is now we introduced a negative stiffness. So this actuator wants to clamp down on the side. This is what the prototype actually ended up looking like. We wrapped it in Kapton tape because we don't want the air gap to go to 0 and have really high forces. So that's a limit on the minimum air gap. And a guy who we work with frequently in our lab, Fred Sommerhalter, did a great job winding the coils and producing this prototype for us. My research, the goal was to integrate that hub into a 6 degree of freedom stage and evaluate its performance. So this hockey puck looking cylinder is the stage. It weighs 10 kilograms, so pretty hefty. The big spider looking thing over it is a pretty large piece, but the only purpose it serves is to place 8 sensors around the stage to measure its position. One of the reasons it had to be that large was we wanted the stiffness to be comparable to that of the stage, so we wouldn't have flexible modes resonating the sensors and giving us bad performance like that. This rack over here has 10 amplifiers, so I also designed the linear amplifier that we use to power each of the coils. There's 6 Lorentz actuators, and then the 4 coils from the hub actuator, which makes 10 coils overall. I'll pause here before I move into the linear amplifier design and ask if there's any questions so far. Okay. So here's the linear amplifier. It's a pretty large board. You can see sticking out underneath. It's a heat sink. So the power stage of this amplifier, because it's linear, is dissipating a lot of excess heat. So it needs to go somewhere. You can kind of it's even in the shape of a feedback loop. You can see, like, here's the input reference. This is the control stage going into the power stage, the current output, and then the feedback to close the loop. This is where you put the power rails in, and these are bypass capacitors, which smooth any deviations in the power input. We added a BNC connection here, which takes the current output and converts it to a voltage that we can easily look at on a scope, which turned out to be very convenient. So, and yes, like you're doing in the design problem, we chose to cross over much higher than the full loop crossover frequency, so that the dynamics of the amplifier didn't interfere with the overall loop. Here's what the actual measured return ratio looks like. We got a higher crossover than predicted and a lower phase margin. You can see the high noise in the signal. It comes from inputting a disturbance into my board, which my board is actively trying to reject. So the signal is low and the noise is high in that relative ratio. And here's what the closed loop look like. You can see, as we're used to, when you have a higher crossover frequency, you get a higher natural frequency than what you're expecting. When you have a lower phase margin, you get a higher resonant peak. So that matches with what we measured in the return ratio. And yes, how I measured this return ratio is that BNC connection, which converts the current to a voltage.
So why do you think the crossover is higher?
Good question. We'll actually address that in the next slide. So this is the plot of the plant. So from the voltage out,
I didn't actually know that slide was coming. Sorry.
Nice prediction. And so I'm going forward in the rest of the presentation. When you see text in black, it's something that I want you to try to think about as I'm going and see if you can answer it yourself. So this is what the plant looks like. So it's should just be 1 over LS plus R. But you see, we have a phase approaching -60 rather than -90. So this isn't really even representable in a simple linear model. And so this effect is what caused, because now I have higher magnitude in my return ratio than I was planning for. So I'm crossing over higher than I was expecting. And the lead filter, or the phase margin that I had designed for, has a maximum phase earlier. So the phase margin is decreasing when I cross over and I get less phase margin. The answer to this is my eddy currents, my Lorentz actuators have a back iron that goes through the coil, and the hub actuator also is coil wrapped around steel teeth. So the magnetic flux is being introduced in steel. And so as the frequency is increasing, eddy currents are generated in the steel, which shield out the magnetic flux and lower the inductance. So you have a inductance that varies with frequency. So this is kind of the control schematic of the amplifier. And yep, you're going to start being very familiar with the control stuff going forward. It's basically a carbon copy of the amplifier you're designing for the design problem. So I had very practical use of this class after taking it last year. We have a differential input to avoid different grounding situations. You can also see here, there's a different color I put for these grounds and these. There's a control plane that is powered by plus or minus 10 or so volts. And then there's a power stage, which is powered by the voltage needed to drive current through the coils, designed for plus or minus 45 volts, but we ended up using less than that. Here's the control stage. I guess don't cheat, but that's the impedance that you should find in your design problem. One added feature here.
Feel free to use it. I mean, yeah.
One added feature here is these Zener diodes. So these are diodes that prevent current flow in one direction, but only up to a specified voltage. So they allow current to flow when you are over a certain voltage. So that's a physical implementation of anti-windup. So if I specified, say, 8 volts as their breakdown voltage, then I couldn't get a control effort higher than 8 volts. So that's what those are for. Here's what the PCB actually ended up looking like. There's this is the Gerber file that we sent to the manufacturer. The reddish color, if you're not familiar with PCB design, is like the bottom layer. There's 2 layers of the board. So that's like the ground planes for the power stage and then for the control stage. We already talked about this, but so there's like a safety feature here, this fuse that will prevent us from kind of, you know, if the power stage were to dump its maximum amperage for some reason, we wouldn't melt the coils, we'd blow the fuse first, things like that. Another question to think about is, for the first 2 or 3 boards that I put together, my resonant peak was higher than I expected and the crossover was lower. So I was shooting for 5 kilohertz, and you can see here we're at 3 or so kilohertz. And I designed for 55-degree phase margin, so the peak is too high. So I was struggling with that. This is where some of the power of this class came in. I modeled changing the values of different features of the return ratio.
By the way, Austin, sorry to interrupt. If you go back a slide, that's the CRT screen of a 30-year-old, maybe older dynamic analyzer, which is like a $30,000 box back when, that HP made back when it was called HP instead of Agilent or Keysight. And we still find it very useful to measure Bode plots with. So if you're stocking a lab and you have some extra money, you can still find these things used, and they're very useful. So that's what that screen is. Now, unfortunately, its I/O is a floppy disk.
Yep.
With a strange little DOS-based code fragment to get stuff from the floppy into a format you can suck into MATLAB. Yep, so we're definitely living decades ago when you pull data off that thing. You have to have saved a few floppies around the place. All right,
got
Austin,
I got
sorry to
familiar
interrupt.
with that. No, that's good to bring up. So here, I just decided, okay, what could this possibly be? So I swept through, what if the inductance of the plant is different than I expect? And just very different values of the return ratio. I found that if I varied the smaller capacitor in my control stage and made it larger than what I was expecting it to be, the shape matches really well with what I was seeing in real life. So it helped me hone in to say, let me look at this capacitor and see if there's a stray capacitance somewhere. It turned out to be that those Zener diodes that I talked about before, when I put them in opposing directions and measured the capacitance across both, I got a stray capacitance of an order of magnitude higher than the capacitor I wanted to use. So it ended up being, I ended up taking those Zener diodes off the board and just limiting the control output voltage by the rail voltage of the control stage.
And I have to admit, I was really surprised by how large the stray capacitance of these Zeners is. But it's in the data sheet when you look for it. And this is the kind of thing you do experimental work, and you have to have your eyes open for things that weren't in your model. The world doesn't know what your model was, and it's doing whatever it does. So you better have sufficient humbleness to go looking for where something came from. And then getting rid of the anti-windup is not that big a deal because you saturate it plus or minus 10 or 12 volts anyway. It's not like floating point words where you can go off to infinity. Analog circuits stop at some level anyhow. So for that, getting rid of that anti-windup diodes didn't matter that much.
Right.
This is why if you want to be a professor, never do experiments, because you can always explain your theory very well and it will always be self-consistent. So if you want a harder life, try to build things, and then you have to learn a lot of things you didn't plan on. All right.
So here's another problem that I was seeing. My DC gains were consistently smaller than I was expecting. It turned out I had neglected to consider that my sense resistor being so small, 0.01 ohms, meant that the trace resistance would be comparable to that of the sense resistor. So I had a resistor accurate to 0.1% of its resistance value, and the DC gain was off by maybe 10%. And it was because measuring the voltage from here added all this resistance of the trace. And so I ended up with a different DC gain than I was expecting. So we spun a new revision of the board and I moved the trace to measure it at the right spot.
So Austin, I can't resist annotating this just to be sure people are what the change was, because this was a subtle one. It took us a while to find it. Here is 0.01 ohms, and you wouldn't think you could buy a 0.01 ohm resistor, but you can, and the reason is to keep the power dissipation very low. And we're using an instrumentation amp, this LT1167. If you're interested in, if you're going to do instrumentation of sensors, instrumentation amplifiers are something you need to learn about. A good example is this 1167. So if you're doing more mechatronic stuff, go read about them. Usually would think of a centimeter or a centimeter and a half of PC board trace being insignificant. But there's 3 amps flowing through here, and we have an only 10 milliohm sense resistor. So a stray 1 or 2 milliohms is plenty to throw off the calibration. The thing you have to do is the high current is flowing in this path. So you need to sense at the resistor terminal. So we move this trace over to the resistor terminal. And that was a subtle one to find out, especially in Zoom land where I couldn't walk in and see the actual PC board. And I think you had to actually point an iPhone at it for me or something. I forget.
Something like that.
Yeah, trying to debug hardware remotely is crazy.
Hmm.
Is that clear to people what the small fix was? That was a 20% cal, because I think you bought a 0.1% accurate resistor.
I did. Yep.
And we were off by 20% in our calibration because of that small PC board layout error. This falls under the heading of 4-wire measurement. If you want to measure small resistances, you have 2 wires for current and 2 wires for voltage. We wouldn't know the calibration, but yes, if you wanted to minimize cost, and the problem would be you would be very sensitive to the thickness of plating. And also, if you buy an accurate resistor, they're also specified, they make them with an alloy that has a low temperature coefficient, because don't forget the resistance of metals changes with temperature. So if you're trying to do accuracy, I would not do a PC board resistor. Plating thickness varies easily by tens of percent. You're not going to be calibrated. And then the temperature coefficient of your resistive material might be much worse than one you buy that's specified. Good question, though.
I see something.
What's this?
Oh, nothing. I'll move on to the next slide.
Yeah. Clearly, I can't resist butting in, but I'll remute.
I appreciate the commentary. This actually, you predicted what I was going to mention here, specifically talking about this HP DSA we have in the lab, which if you wanted to look at the actual layout, lots of great buttons, but also this is the BNC output for the excitation signal. And then you're comparing an input and an output signal to create your Bode plot. This is a tricky one to think about. In reality, measuring the return ratio of the loop. How do you, so for the closed loop measurement, you just excite the voltage reference and measure the current out. But for the return ratio, you have to break the loop somewhere where you can read the signal properly and then measure at 2 different nodes of the loop, but still get the full loop. So it's a little trickier. The way we did that was solder an additional input resistor to the power stage. So now the power stage is a summing junction of the control effort and an excitation signal. And then you measure the voltage at the output of the power stage and the voltage at the output of the control stage. When you compare B over A, you get the full loop without the gain of the power stage, which the gain of the power stage is we assume it's a constant 4 magnitude gain. Now that assumption is safe because of the dynamics of the op amp, but it is an assumption in the return ratio measurement. So basically I took B over A and then multiplied it by 4 to give me my overall return ratio. Any questions, last questions about the amplifier before we move on to the overall levitated stage? Okay. So next was building the stage to put the hub actuator in. Already talked about the setup here. These wires coming down. So the Lorentz actuators we used, we already had them in the lab from other experiments and demos. They happen to be much larger than we needed. And their largeness meant that the back iron was very heavy and would have added a ton of weight to the stage. So we ended up levitating the coils, which you wouldn't do in a manufacturing level version of this. But so these wires are the attachment to the coils. There's 4 wires coming out of each coil, 2 for the current, and then 2 for a thermistor that we put in to the coil to measure its temperature so we don't overheat things. I hadn't mentioned this before, but you can see here, this is an aluminum stage, but there's these little steel targets. The eddy current sensors have a larger like they can measure a larger range of distances when they're reading off of steel than aluminum. So we needed that full range, so we use steel targets. These over here are Lambda power supplies. They're great. You can get them on eBay for like 150 bucks each. And I used 4, so 1 for the positive rail voltage, 1 for negative for the Lorentz actuators, and then 2 more for the hub. This was the power supply for the control stage of the linear amplifier, so plus or minus 10 volts. And then here are the breakout boxes that we use to send signals to the amplifiers and then read the signals from the sensors by the controller. Here's the return ratios we got for the hub actuator, the X and Y degrees of freedom of the stage. You can see it looks fairly close to what we wanted. The original target crossover frequency was 150 hertz. I ended up so far settling for 100, hoping to push that up a little bit, but you can see that there's this phase fall off, which is faster than what I was expecting. This model contains the time delay from the control loop. So I'm still trying to trace through and figure out what the extra phase shift is from, and that's consistent through the different degrees of freedom. Here's what the other 4 degrees of freedom look like. Again, settled for lower crossover frequencies than I wanted. The rotational degrees of freedom, we went down to 80 hertz, and then Z we kept at 100. You can see also, in addition to the high frequency phase shift, the Z degree of freedom particularly, but the other ones as well, have this low frequency leveling off. So maybe I'll bring it up at the end, but you can think about what dynamics might cause this low frequency behavior. Here's what steps of the stage look like. So I hadn't addressed this yet, but this is a multi degree of freedom stage, and I'm trying to control it with our kind of classical single degree of freedom controllers from this class. So coupling is an important thing to think about, and we're hoping to design controllers that are sufficiently decoupled. So looking at these steps and then seeing the response of the other degrees of freedom is important. So you can see out here, like when I take a step in X, theta Y has a response. When I take a step in Y, there's this response in theta X. And that makes sense if we're applying a horizontal force to the stage, but we're not doing it through the center of gravity, we're going to induce a rotation. So you can see that result show up. You can also see the steps aren't matching the model very well. That's because my control effort was saturating at this level of step. I can bring down the step that I wanted to look at a linear step, and it looks closer to what you expect, but the noise floor of the hub actuator is such that if I reduce it down to that level, it doesn't look very good on a plot. So I just brought it out, made it nonlinear and saturate, just so you could see the decoupling. Here are the other 4 degrees of freedom. I wasn't saturating in these, so it matches the model better. You can see clearly there's some coupling between Z and the theta degrees of freedom. I'm taking a step in theta and seeing the Z response, and that showed up in debugging the 6 degree of freedom stage later. Before I move on, I'll pause here and ask if there's any questions so far. Oh, okay. So here's the mechanical stage. Tom from Professor Slocum's lab did the design work on this. Great job on the design. It was 17-inch round aluminum stock, which was machined to put in these pockets to fit in the different Lorentz actuators. The big circular pocket in the middle is for the hub stator to fit up into the middle of the stage to try to act near the center of mass. These different pieces were glued together. Here's the Lorentz coil configuration. You have 4, which when you act in common mode give you Z, and then you can act in pairs to give you theta X and theta Y. And then we just used a simple pair of Lorentz actuators to give us theta Z. Oh yeah, an important thing to mention. The design was targeted so that the first flexible mode of the stage was above a kilohertz. So you're seeing in the design problem, the way that resonance is close to your crossover can affect your performance. So we wanted to push those resonances out an order of magnitude beyond our crossover, just so we didn't have to interact with them very much.
Are you going to mention the little brace?
Yep, that's important to mention. Good point. If we didn't support the hub actuator at the bottom, it would look like a cantilever of just mass suspended from the top skin of the stage. So it would have this low frequency drum mode. So it was important to have a rigid connection from the bottom of the hub to the bottom of the stage. So that's what this kind of extra adapter piece, and then these cross mounts, which mount to the bottom skin of the stage.
Yeah, when you're designing stuff, really watch out for cantilevers. They are bad dynamically. So I'm just annotating, and it'll just change colors. That with that version, I think the first modes were only like 600 hertz or something. I forget, Austin, they
Right,
were a lot
right.
lower.
They were,
Which basically this little skin twisting with this hub. This is a lump of steel and magnets, and it wants to basically go at angles like that and twist the top of the skin. So you know, you get a sensitized to cantilevers are a sort of beginner's favorite design element, but they're really bad in terms of dynamics. So a little plate, whereas things in tension, like think of a piece of paper, it's got no bending stiffness, but its tensile and shear stiffness is very high. So if you can get skins in tensile stiffness, you can very little extra mass, you can change the modes a lot. That's kind of a generic lesson. Okay, I found myself unable. I made it through about 5 minutes of not saying anything, but I failed.
I appreciate it. I appreciate the color commentary.
You know, I have to say it's a lot easier than lecturing to just jump in and stuff, and I got to figure out how to get this gig.
So here's the thermal considerations. We thought about doing gravity offset. So having a permanent magnet configuration, which offload the main weight of the stage, and then just using the controllers to operate around that operating point. But since we had these, and that's how in a production level machine, they would definitely use gravity offset because we're trying to be efficient. And so you don't want to use current to levitate the weight of the stage. You want to operate around an operating point. But because we already had these Lorentz actuators, we just used them and ran. It turned out we needed about 1 amp of current constantly through those 4 Z coils to give us levitation. So this was another of Tom's designs. This is looking at the temperature as we run 1 amp just through the coil by itself. And here is when we run it mounted to the stage. There was a, a consideration. We have this 3D printed. We did use high temperature resin from the Formlabs printers, but it's 3D printed, so a lower, melting temperature. But if we potted it in thermal epoxy, so it's conductive, and then had a aluminum connection to the stage, so we can dissipate heat into the stage, which is then kind of our big heat sink out to ambient. You would not want to do that in a real stage because the temperature variation is going to change the location of the wafer and shift things around. So that's why you would put the coils on the stator in the real world, but we just put the coils on the mover for this demo. Also, if you're wondering why did we split the top mount here in half, it's to prevent eddy currents when we're driving magnetic flux through the middle. If this was a closed circuit, then it would create eddy currents to, oppose the magnetic flux and reduce the effectiveness of the actuator. So that's why it was split. Here's where we placed the sensors, which you already saw in the sensor layout. You can see here, there's kind of this sweet spot in the middle of the stage for the vertical down-facing sensors, where the first 3 flexible modes were did not excite this ring in the middle. So that essentially made the modes unobservable. Professor Trumper talked about that with the fast tool servo. The X and Y sensors can observe clearly if they're kind of in this maximum movement area of this mode. So we had the option of putting in additional sensors on the other side. And if you think about if I take X as the differential between those 2 opposite side sensors, then I'm rejecting the common mode flexible oscillations of the stage and just looking at the X translation. So we had that as an option. We ended up not needing to use those, but in case we needed them. And then yes, measuring the rotations was just looking at pairs of sensors and measuring them differentially. Here's how we went about calibrating the sensors. I have an aluminum piece here with the steel ground target, just like the stage, that I mounted in a Bridgeport in the LMP. I took 200 micron steps of the mill and then just manually wrote down the voltages at each position. The circles are the data points that I got for that. So kind of a linear region, but overall a nonlinear sensor. So I did 2 fits. One, this like a linear fit for the middle range of the sensors, and then one, this higher range cubic fit. We like to avoid nonlinear things because if I cube the voltage, I'm also cubing the noise of the voltage. But we had this option if we wanted the larger range. We've talked in this class about anti-aliasing when you are converting from analog to digital. So that's what this is. The breakout boxes have, so these are shielded cables with the sensors coming in, and then they pass through an RC circuit, which the time constant is set to be 10 times higher than my mechanical crossover frequency. So I start reducing the magnitude of frequencies coming in higher than that. So I avoid aliasing in my digital controller, and I avoid looking at signals that I'm not interested in. An important thing that I took away from this process also was to use, at least for this setup, I use simultaneous sampling. So my digital reading of the sensors, I do all at once rather than sequentially. When I was originally using a multiplex card, the high impedance of my sensor and a small capacitance in the card itself creates a time constant which is large enough that moving the voltage in one sensor affects the readout of the subsequent sensor, because the multiplexer is taking steps of voltage to read the different sensors. So I avoided that problem by using a simultaneous sampling card. I could have also done it by making my sensors low impedance, passing their output through a buffer circuit or something like that, but that's the way that I went about it. Any questions so far? All right. Here's how I did the decommutation, which just means I had 8 sensors here, a vector of them, and then I wanted to convert them to the 6 degrees of freedom. So it's just simple geometry. You can see here Z, I'm just averaging these 4 middle sensors to give Z. Theta, I'm using the small angle approximation, so just a simple difference. Here's what the controllers looked like. This is not exactly my controller. There would have been too many lines on it with all the different degrees of freedom.
By the way, could we go back a slide?
Yep.
I would call it decoupling rather than decommutation, just because commutation has this sense of motors.
Right. Okay.
Just linear decoupling. If you think of rigid body for small angles, you can just take differences in simple ways, and sine theta becomes theta, and all that becomes this. So they're just simple linear transformation matrices for small rotations. If you're doing spacecraft attitude control, you got to get into the real. If you have large angles, you got to get into coordinate frames and how you define them in a unique way, and do you use Euler angles or quaternions or such. But for these little tilt things, then a linear transformation decouples.
Right.
Okay, thanks.
So yeah, here's what the different, trying to use CISO controllers to control a multi-degree of freedom stage. I included in this diagram a feed-forward term that we could have used. You know, if you take a step in position, you can predict the acceleration force that you need to take that step. We didn't use this feed-forward term, but basically you have controllers that operate for each degree of freedom. So 6 individual controllers. They then go into this, I'll call it coupling rather than commutation, which convert the control efforts coming out into the various voltages that are needed to be sent to the linear amplifiers. The amplifiers just convert those to current using what we approximate as a DC gain. The currents go into the plant, and then the plant responds by changing the sensor values. And then I decouple those sensor values to turn them back into degree of freedom measurements, which I can then compare to close the loop. I designed the controllers for the stage the same way you've been doing in class, just using MATLAB transfer functions to take my crossover frequency and phase margin and determine the actual Kp, Ki, alpha, tau parameters for the stage. For the hub actuator X and Y, I ended up using 2 lead filters rather than 1, so 2 in series. And the reason is phase margin is basically a way of accommodating uncertainty. And because the hub actuator is nonlinear, you can think of it as the hub actuator as having a negative stiffness, but the negative stiffness is varying with position. So to accommodate for the uncertainties of the hub actuator, I added another lead filter to give me more phase, which was helpful. Here's how we did the commutation or coupling to take the degree of the control efforts for each degree of freedom and put them into the different amplifiers as voltages. On the right first, the Lorentz actuators is another just simple geometry. So for instance, I have a current output that I want for Z, and I put 1/4 of it in each of the 4 vertically oriented Lorentz coils. And the output units of my controller was voltage. So in my plant model in MATLAB, I considered the output being voltage, multiplying it by the DC gain of my linear amplifier, and then multiplying it by the force constant of the Lorentz actuator, and then going into the plant, the free mass of the plant. The hub actuator, we used this experimental data where we had seen the relationship between current and force. And so we used the units of force in the controller output and then converted that into the current that we needed to send to each of the coils. Because it's not really that easy of a relationship, the hub actuator, if you apply current and you're at a different position, you'll get different forces. But the beauty of linear control is that we can just treat that as a disturbance into the plant and our controller will handle it. It's also interesting here, like I can basically set the units of my controller effort as whatever I want and then use the gains of my loop to sort it out. So if I set this output as force, then in my model, I'll just say that my controller is directly acting as a force on the plant rather than going through the voltage to current conversion and everything, and the units work themselves out, which is pretty cool. Here's the plant models that I used for the controllers. We've, in this class, a lot of times used the plant of a magnetic levitated system, which has this S+ pole and S- pole, and I had never bothered to think about why that is. But it turns out if you just use a mass spring oscillating system, but the spring is negative, this plant is what comes out of it, the X/F transfer function. So in case you were curious about that. And then the mass of the Lorentz actuators is just a free mass, which is the benefit of a levitated system. I have no kind of stiffnesses to worry about, damping. I'm just acting on a free mass. Here's what the controller looked like in LabVIEW. Here I'm comparing, the blue line is the model of my controller, and then the yellow line is the Tustin discretized controller that I actually measured with a dynamic signal analyzer in LabVIEW. So you can see very similar, and then some deterioration at high frequency. And then this is what the LabVIEW code actually looks like. It looks just like what we have been doing in class. So we multiply by kPa first. We break out the integral by itself so that we can set anti-windup. We add it back in and then run it through a lead. My hub had a second lead, and then I added a low pass filter at the end to reduce, to increase my noise attenuation. diving into one of those controllers specifically, this code came from Bridge and Tyler in the lab, and they explicitly do the discretization that we've learned in class. So this is the LabVIEW implementation of a difference equation, which is taking the continuous transfer function and then mapping it to its difference equation. I know this is ugly. I did not clean it up, so I apologize for that. But this is what my right loop of my controller looks like. And if you squint, you can see the shape of a control loop. We have references being generated here. This is the difference that's comparing reference to feedback. This little box converts the sensor voltages into positions and then makes the difference here. It passes through a controller for the hub and then the controller for the Lorentz actuator. I added these switches that allow me to turn on and off each degree of freedom as needed. And then these in blocks are what do the commutation to go from the degrees of freedom to from the degrees of freedom to controllers to the voltages that I need to send out. Yeah, an interesting thing is, so I have the ability in the code to read the sensors at 20 kilohertz, even though I'm only writing at 5 kilohertz. So that wouldn't be beneficial, except now I can run a 4-point moving average of the sensor values. And so I lower the noise of the sensor readout. So I basically, each sensor measurement that I'm reading in the loop is the previous 4 sensor measurements averaged. So I get closer to the real value, which is good. So now we'll get into the debugging of the controllers. Any questions here? Okay. So
I'm the only one that asks questions, huh? Nobody else has any curiosities.
So here's the debugging process. It was very interesting, and this is an important thing that I learned in debugging controllers. So I started here. You can see if you can look here, you can see this dummy mass. So we didn't put the hub actuator in at first. Because of that negative stiffness, it makes it more tricky to control. So we figured, let's control the 4 Lorentz degrees of freedom first. And once we get them operating the way we want, we'll put the hub in and then do the full 6. So when I first turned it on, it was just oscillating like crazy, did not match at all what I was expecting. So it was actually Bridge who gave me the advice. Definitely turn off your lag filter. Your integral is adding DC gain, but at the cost of reducing your phase, which you don't want when you're just trying to stabilize the system. So turn off your integrator, start with just your lead filter, and then you don't know exactly what the plant's doing. So start with a KP of 0 and slowly raise your KP until you get stable, until you get a stable response. As soon as you're stable, you can measure your return ratio in plant Bode plots and get a feel of what you're actually looking at. So when I was first doing it, I found a KP value 3 orders of magnitude smaller than what I was expecting, gave me stability. And it turns out that was just a units error of my model being in units of meters and my controller in millimeters. So, but it was helpful to go through this process to get stable so I can figure out what the problem is. While I was just doing the Lorentz actuators, I had this funny problem where each rotational degree of freedom was stable, but when I turned them all on at the same time, I would get this oscillation, and theta Z was the worst. And if I zoom in, it's the kind of constant frequency oscillation. I still don't know exactly what's going on, so I kind of hand wave and say it was MIMO interactions. But the way I got around it was increasing the phase margin of my rotational degrees of freedom and then lowering their crossover frequency. Once I did that, it was able to eliminate this extra oscillation problem.
Yeah, as a comment, this MIMO decoupling works pretty well, but there's no firm guarantees about stability because you never get the decoupling working perfect. So driving one axis drives the others, and that then gets into the other loops, and you can easily get instability from this residual interactions. That this is the nice thing is CISO controllers with roughly decoupled loops are pretty easy to debug. The downside is you're not fully encompassing the MIMO aspect of the problem, but we managed to hack our way through this way. Whereas if you just fed all this into a MIMO LQG design problem and you get a controller and you run it, it's unstable. You really have no idea what to do next. This lets us kind of work our way up through getting things to operate.
Right.
Also nonlinearities like in the hub actuator, and yeah, and dynamics as you might have different breakpoint frequencies on different of the actuators, so then the forces you think you're making aren't dynamically equal. And there's a lot of places where this simple idea falls apart, but it gets used a lot for maglev stuff. This is really one of the standard solutions, and we've used it in a lot of different contexts, this idea of decoupling.
So I'll move on now and talk about what it was like to put the hub actuator in. So this is what I wrote in my notebook as soon as I thought I was levitating in 6 Degrees of Freedom. Very excited. And then I took a second longer and looked at the data, and it just looked terrible. So I'm commanding an X sine wave. I'm getting this really terrible Y response as well. The plant looks nothing like what I expected. Then actually it was Christian who gave me this advice. He said, try looking at the efforts that are being outputted from your controller, because the hub actuator has a magnetic center where you don't need a steady state force to keep it there. Because in the exact center, the bias fluxes are all equal through the air gaps. So in the precise center, you don't need a constant force to hold it in its position. So he said, try moving until you get to the magnetic center and see what's going on. So when I did that, whenever I would get close, I would start oscillating. So I realized I must have been touching down when I thought I was levitating, touching down on the side, and I wasn't actually levitating. So I redid that process of starting with the lead, increasing phase margin, sweeping through KPs, and then as soon as I got something stable, marginally stable, I measured the return ratio, the plant, and then was able to, from there, know what I was doing to pick the controller values to get good performance. This is my more muted celebration after being humbled. And this is what, like at the very beginning, as soon as I levitated, this is the decoupling that showed up afterwards. So like, okay, that looks like what I would want it to be. The plant looks like a typical negative stiffness plant starting at negative 180-degree phase, although I did model it with another high frequency pole, which I still don't know the exact mechanical processes that are causing that. And then some, extra high frequency phase drop. That is one of the problems I'm still thinking about right at this moment, is if I measure the plants for each degree of freedom and I model a 700 microsecond time delay, then it matches pretty well with the data. But I don't know where a 700 microsecond time delay could come from. Perhaps it's my lab view through the process of reading and writing, doing multiple control loops before it actually outputs. So it's a longer delay than I expected, but I'm still investigating that. Another question I'm still thinking about, which I had mentioned earlier, is this, especially in the Z degree of freedom, a low frequency difference from what I expect. So it turns out when I added into the model, instead of a free mass, a mass spring damper, then I could tune it and it would look basically exactly like the data. So there is a spring somewhere in my system. Not sure exactly what it is. I've thought about a lot of different things. Could it be the cables of the coils pulling on it? Could it be the variation in Lorentz force as I move up and down through the stroke? Still trying to figure that out. but I guess that such is life doing experimental work. So that is where I'm at right now. And I'll leave you with a little GIF of it rotating in theta Z. So thanks for listening.
Nice presentation, Austin.
Thank you. I started my master's in 2019 in the fall, and it's taken till I levitated a couple weeks ago. So it was a very fun few weeks to go from all the prep to getting it levitated and measuring Bode plots. That was a really fun couple of weeks because it happened pretty fast. Thanks for asking.
Yeah, hardware-based projects don't necessarily go quickly, but you learn a lot from them.
I do have a pair of fans that I run when I'm running the stage that pull air through and cool so there's the heat sinks attached to the bottom of them, and then I'm running air through to cool down those heat sinks. Good question. Great point. Yeah, well, so you actually do want to measure exactly where you care. You care about the precision at the top of the stage. But you're right. So there's light coming in there too. So you have to worry about that. The requirements that we were given were work on the stage and just assume you have a perfect sensing mechanism in the real world. So we didn't bother actually thinking about actually implementing the sensing system that would be used. But you're right, that wouldn't work, having some big structure above the stage.
In a real stage, you would package the sensors inside because you would want the relative gaps measured. But then there's always a sensor that measures to the wafer. A lot of times there are alignment marks on the wafer itself, and you print each chip field relative to its alignment marks. And those these days are 6 degree of freedom alignment marks. So it would actually be nested metrology of local sensors by the actuators to control the actuators, and then the workpiece metrology at generally a bit lower bandwidth, measuring to alignment marks built into the chips as you print the first layers. So you're quite right. We would want relative gap sensors in the actuators built into the underside of the stage, but there was no point in doing that right now because it would take a lot more effort, it'd be hard to package, and it really would prove nothing different. And we have right now the free top surface, so we just took the easiest way.
That's a good question. I mean, yeah, you can't, if you care about the performance of the top surface and the actual accuracy of the top surface, then you can't neglect the resonances that are affecting the top surface like you can if you just want to levitate the stage. So that's a good point. I guess in the real design, you would want to have a stage that.
I think I would jump in there because
Yeah.
these are modes at a kilohertz, and there's no way we have a loop with control authority at a kilohertz. So we're never going to be able to do something helpful to those high frequency modes. At that point, a controller can only do things that are bad if you let those modes stick up these are lightly damped modes, and if we let them be observable and controllable, then in the Bode plot they'll have sharp spikes and they can make the loop unstable. If we make them unobservable, we can't excite them around the loop. The feedback loop can't interact with them to get them ringing. So for high frequency stuff, you really want to make your controller blind to it. Now the question then is, what other disturbances exist, and what is the spectra of those disturbances? Like if somebody's tapping on the stage with a ball peen hammer, that's going to keep it vibrating. And if your requirements were to prevent that, you have to come up with some other fixes. One of which is to build, say, for instance, constrained layer dampers into the stage. You make some layer of viscoelastic shear material and then a capture layer of metal, say a thin aluminum skin, and you make the stage broadly well damped. So then these lightly damped modes become well damped, which is probably a good idea anyway. So one strategy is then to build passive damping. Another which I've known is I've seen what are called the vibration absorbers. You build tuned mass absorbers, little mass spring sets that you put in the stage that have a resonance that turns out to be an anti-resonance to the stage resonance. It means if you get vibration, there's a loss mode into this tuned absorber. If you want to learn about those, the problem is those are specifically tuned and they have to be matched. But I've seen stages where there's 2 or 3 or 4 little tuned absorbers built in to null some modes. So there's a subtlety to it, and this whole area of vibrational modes and the dynamics in control loops, something well worth learning about. And I'll list some references for people after we finish with Austin's talk.
So Tom, the guy who designed the mechanical stage, actually did the measurements to compare the model with the stage. So it is hard because you're trying to look at the resonances of a levitated stage, and we haven't levitated it yet. So he would put it on foam or springs and then just hit it with a hammer and do the FFT to look at the response. And he would, so to excite one mode in particular, he would suspend it in areas that would be nodes of that resonance, and then hit it in an area that would be an antinode to excite that resonance in particular and measure it. So we found that, you know, we designed for all of them to be above a kilohertz. Then 2 of them came down to be in the 900 hertz range, but still really, he did a good job and they turned out to be really high. So. Exactly. Yep.
Yeah, there's a whole body of knowledge and expertise called modal analysis. And the people that do that, the dynamic analyzer that we showed you can be used for modal analysis also, or you can do data-based. And typically you have a little instrumented hammer with the load cell on it, and you tap things. And that force of the impact is recorded, and then you have accelerometers scattered around the structure of a machine, and you look at the response, and there's math that goes with then deducing the mode shapes and frequencies. And typically you put a bunch of accelerometers. If you have a lot, you put them all at once, and then you tap different places and get a whole modal structure and all their frequencies. Or you tap somewhere and move accelerometer around, and it typically stick it on with like sticky wax, or you bolt down with a bolt. But there's people whose whole lives are practitioners, consultants in modal analysis. So large structures, machine tools, aircraft, other things where you care about the vibrational modes, you could hire a consultant or read the theory for yourself and do modal analysis, which is it's something. Yeah, there's a lot of well-written stuff on that. It's not my expertise. We usually get it from our Bode plots because we can drive a system and measure it, so we don't need to do modal analysis. The problem is before you levitate, how do you get the modes? The really key thing is when you're going to do when you're in the CAD level and you have this is what I think my machine will be. You can extract the first 30 modes out of some FEA program and then predict them and put them into a MATLAB model and look at your Bode plots and decide if that's something you're going to be happy with.
We did try looking at, you could put like position measurements in your FEA at mesh points where you think you might put your sensor, and then go through the different modes and look at what that actual sensor readout would be to look at your predicted Bode plot of putting your sensor there. So it's helpful to see where you could put the sensors. I mean, I still haven't figured out, like that last slide I showed, I still haven't figured out some sort of low frequency input that's happening to my stage in Z. But when I'm doing the sweep to look at the crossover frequency, by then the resonance has already happened and I'm on the mass line of the Bode plot. And so my performance isn't really negatively impacted there when I'm trying to push the performance out to the crossover frequency. So we talked about also for the gravity offset, we were thinking an easy way we could do it if we were worried about the current dissipation is rather than levitating the whole weight of the stage, we could put the stage on foam balls, which is basically like a low spring coefficient spring. And so you have now this resonance from the spring, but that resonance is at low enough frequencies that you don't care about it when you're crossing over. So that was an option to do gravity offset. I think vibration isolation tables and stuff kind of rely on low resonances. You have like a spring isolated system so that now you quickly get past the resonant mode, and at frequencies you care about for the disturbances, you're on the mass line. And so you're falling, the magnitude of the response is falling away quickly. So in that sense, a low resonance can be helpful.
Yeah, low frequency rigid body modes tend to be not a problem because above them you're a free mass, and that's an easy thing to control. That's your almost ideal world. Yeah, so when you're above a low frequency resonance, when you're above it and you cross over on the 1 over m omega squared line, the low frequency mode is gone because your controller moves it. Think of your controller adding a lot of stiffness, so that low frequency mode moves away, and it's not a problem.
I guess it's a question of how far do you take each parasitic thing before you can choose to neglect it. So if I look at like the gain of the op amp, do I have to include it and its dynamics, or do I neglect it? So I clearly didn't do a great job of that, in that I had parasitic effects showing up like I didn't expect, which means I neglected them too fast. But you should go through and do kind of a back of the envelope calculation to see, does the dynamics of my op amp, for instance, affect me at the low frequencies where I'm trying to cross over, low frequencies relative to the op amp. And so typically, like in my case, I could say, no, they don't affect me. I can just treat the op amp as an ideal one. So yeah, you should do those little back of the envelope things before you start throwing out those effects in your analysis.